Yes, my name is Seán Brennan. I was invited here because Tracy and I got into a fight and I had to make up for it somehow. So I'm here with you today to talk about some of the major work that I've done as part of my PhD, which, as I said, I'm finishing up in about 2 weeks. Just a note to Tracy, I can't actually see you. So if there is any issues, please just make yourself known, just with the presenter view. So there's a lot that I'd like to cover in this talk. And there's a lot of details I should go into, but of course there's no need. And of course, if there's any questions, please throw them in the chat or send me an email afterwards. I'd love to discuss things further. So this talk is going to talk about massive stars. So I thought I'd start off with kind of a simple question as to what exactly are massive stars. So we're all familiar with our sun, and we classify this as just a one solar mass star. So we measure everything based off the mass of the sun. As we get larger and larger, beyond about 10 solar masses, up to, well, we don't really know the upper bound, but up to maybe 100, 200 solar masses, these stars act in ways that are, well, very, very unlike what we'd expect the sun to do. And these produce a plethora of observationals that we can see with telescopes on the ground, as well as space telescopes. And we're going to talk about one of those very important ones, which is the Hubble Space Telescope. Most talks should go over why their research is important, so I will talk about why massive stars are important. And I thought the best way to do this would be actually look at this periodic table. So the periodic table was designed in the late 1800s by Dmitry Mendeleev, based on observational properties of each of the atoms. I think it was actually based off the spectral properties of each atom. We now know, part and parcel to the development in astrophysics, where some of these atoms come from. So this plot is a little outdated, but generally we have hydrogen and helium. Also due to cosmic rays, which I won't get into. And then the majority of the rest of elements in the universe are formed from stars, and the vast, even so, most elements are formed due to massive stars and how they end their lives as supernova. So you can always think that the iron that's used in buildings or the gold on a wedding ring came from, at one point in our history, the inside of a massive star, and that material somehow made its way to Earth. So that's one reason. Another reason, which I like in particular, and it gives me an excuse to show off some nice pictures, they're kind of like, I like to call them the kind of gardeners of the universe. They shape how galaxies and dust clouds appear to us. So here we have two images from the Hubble Space Telescope. On the left is optical, so what we could sort of see with our eyes, and then in the infrared, so at longer wavelengths, stuff that we can't really see without special equipment. And you can see here that the shape of these, what are called the pillars of creation, which are massive columns of dust, their shape is defined by massive stars around them. So when I say massive stars, I mean very heavy blue stars, and because they're blue, they release a lot of UV photons or UV flux, and then this flux can disintegrate and dissociate dust, and you get these really interesting shapes. And just on the left-hand panel, just in the circle, you can actually see some of that material being, you could say, blown off these dust columns, and it gives a really interesting shape. And this is found all over the Milky Way as well, the local universe. We can see the influence that these massive stars have. So I mentioned in one of the earlier slides that these stars behave somewhat differently to our sun. So this slide is trying to condense stellar evolutionary theory into a handful of lines, and we're just going to focus on the most important bits. So all stars will fuse, like our sun, fuse hydrogen in their core from nuclear reactions. And this is the energy that supports the star and produces sunlight. As the star progresses, it will fuse heavier and heavier elements in its core. So it starts with hydrogen core burning and moves to helium core burning. At this point, our sun won't be able to progress further, and it will end its life in a different pathway. But for massive stars, due to the material that makes them up, they can continue burning material in their cores up until iron. And they're able to do this by compressing their core and increasing the temperature. And by increasing the temperature, you can allow these reactions to take place. Because of their mass, and I've included one equation here just on the bottom right, because of their mass, they live very short lives. So if you take the lifetime of our sun, again, a 1 solar mass star, which lives for roughly 10 billion years, you take, say, a 15 solar mass star, so 15 times the mass of our sun, you'll live for a few million years. And you can see here in this table that as you move from different burning stages in the inside, in the core of the sun, these stages get faster and faster. So the majority of the lifetime of a massive star will be under hydrogen core burning. And then as you move to helium, carbon, and neon, it gets shorter and shorter. And then once you get to neon, oxygen, and silicon, the final stages of burning, you get to burning stages that are roughly within the lifetime of a human. So the star, the inside of the star is evolving at the same rate kind of we are. So what happens when we get to silicon core burning? So silicon undergoes nuclear fusion and results in a very dense iron core. Because of the chemical properties of atomic iron, it can't undergo any further reactions to produce energy to hold up the star. And the way I like to think of this as, if you're holding something up, I should have a tennis ball, but I just have this little trinket. If you're holding something up, and you can imagine my arm here is the pressure from the core supporting the star, all that mass above it. When you remove the support pressure, everything just falls down. So once you get this iron core, you get all the material that's on top of it, which I'll refer to as the envelope, basically outside of the core. You get this material crashes down, basically falls inwards at a very high speed, up to 25% speed of light. Once it hits the core, like our tennis ball, say, hitting the ground, it just bounces back off. And of course, things are very much more detailed, but for the purpose of this talk, this will do nicely. So what happens after this material bounces off the core? So we have a nice little animation here to show this. You get your material falls inwards, proceeds to bounce off the core. That drives a shock wave out into the envelope, out into the outer layers of the star. And then this shock wave disrupts the star, basically explodes the star. And you're left behind with basically a mess. You can see in this animation here, you have all this blue material that's ejected outwards. This is from the inner layers of the star, all these nuclear ashes that were burnt beforehand. And you get what's called a core collapse supernova. And for the rest of the talk, I will signify this as the death of a star, although it can leave behind some compact objects, such as a neutron star or a black hole. This is an animation in the background, but thanks to Hubble, we've actually been able to observe basically an ongoing supernova. So our most recent and our closest supernova was called 1987A, which happened in the Tarantula Nebula of the Large Magellanic Cloud, one of the satellite galaxies to the Milky Way. It was the first supernova in 1987 to explode, and fortunately, it was extremely close. Being so close, rather than observe this supernova or the star as just a speck of light, which is what the majority of our supernovas look like, you could call it just a single bright pixel. Because it's so close, we were actually able to resolve it. So on the left or the right-hand side of your screen, on the left-hand side, I have a before image, which is how the environment looked before the supernova before the star underwent core collapse. And then you can see on the right-hand side, you have this bright explosion, which was the star ending its life. And because the Tarantula Nebula is so close, we were lucky enough to know where to look or to have images of where to look before we actually went core collapse. But with that information of what the star looked like, we found something very strange, that the star didn't look like it was about to explode. If anything, it looked like a young star. So this kind of highlights either our stellar evolutionary theory is wrong, or there's some key point that we're missing. And to address the latter, if there's something we're missing, we can look at the supernova years and years after it exploded. And this is where Hubble came in. So Hubble took this fantastic image of the remnant of 1987A. And if you look at the center of the screen, you see this weird shape. And I've included two cutouts here. So on the upper right-hand side, you just see a zoom in of that shape. and you can see there's circular features. And then on the left-hand side, I've included an artist's impression of this shape, and the whole system's been rotated, so you get a better idea of what's going on. So rather than our, let's call it a trivial example of a star exploding, which is you have a circular star and it explodes, and you have a circular distribution of, or spherical distribution of stuff, of ejecta, of material, we get this weird, what's called an hourglass shape, where you have these 3 rings, and this whole shape in general is very strange, and you can't explain this for a single star evolving on its own to do things like this. And one of the most common scenarios is to actually include a binary companion. I will return to this a lot later, but essentially you have 2 stars that evolve or spend their lives orbiting around each other, and as one star evolves to later stages of its life, you have these stars begin to interact. And this interaction can change how the star lives and evidently how it dies. But I feel that this slide and what I've just spoke about highlights an amazing problem. It's not always clear if a star dies. If 87A was observed in an extragalactic setting, we wouldn't be able to achieve these the details or the privilege of looking at it after it explodes and being able to resolve that. And most of the time, the transients or these explosions that we observe are from galaxies that are too far away to actually be able to get any amazing detail. And one example of that, well, that is in our own galaxy, and that will address kind of the main topic of conversation for this presentation, is the Eta Carina system. So this was a star that, obviously, you can see these pictures from Hubble in your center screen, underwent some type of explosion that pushed it out of some, steady state. But we know for a fact that the star has survived. So on the right-hand side here, I have a composite image. So these are images taken in different colors, and then we combine them to show you roughly what the system would appear like to your eye. So we have optical, ultraviolet, and X-ray data in this image, and you can see where regions glow the most. And we can use this information in these different colors to study the object and how it exploded. In the top left, I show you that this system is still evolving. So you can see here over roughly a 10-year span, the whole explosion is still expanding out. So this tells us that whatever happened must have been quite recent if it is still expanding and still dense at this time. And the lower left, this is fantastic. By using these different colors from Hubble and using a little bit of maths, we can actually model how this system appears. So usually science is a visual endeavor. We see a plot or we see an observation. By doing tasks like this, we can actually extend this out to how are these systems modeled? How will they feel in our hands? And it's an amazing progress that we've made using information from something like Hubble. So what happened to the system? We know that in the 1840s, this object, which we now know is a binary system, a modern day binary system, underwent some type of explosion, which has been dubbed the giant eruption of the 1840s. Using Hubble, we can actually peek through all this material that the star somehow ejected out about 200 years ago, and we can see that there's a star surviving in the middle. So unlike 87A, where we can actually see that the star is in fact gone, with this case, we know that the star is still there, and something caused it to release roughly 10 times the mass of the sun into this strange shape with a supernova-like energy, so something similar to 87A, but the star has survived. And this is the main point of, or the main topic of controversy, is this this non-terminal explosion. Excuse me. So we like to classify these type of eruptions where the star survives as a supernova impostor, and this will be the main point I will get onto a little later. So just for fun, one of the main scenarios to explain the Eta Carina system actually involves not 2 but 3 stars. So here's an animation showing how we can explain the observables of the car. It involves 3 stars, one of which evolves and expands into a supergiant, interacts with its primary, and you can see that here a star is ejected out of the system on a very eccentric orbit, and you're left with this binary system. These 2 stars will eventually merge, and from complex hydrodynamics will produce the overall morphology of the Eta Carinae system with a secondary star orbiting it. And this is how we perceive Eta Carinae today, and it can explain most of the observables. How we can have a supernova-like explosion with an asymmetric distribution of material, as we've seen from the Hubble images, with a modern-day binary system. So moving on, we have the talk of a supernova versus an impostor. So as I'll just reiterate really quickly, supernova, we have our progenitors destroyed. We are able to see the material from the inner regions of the star, so these carbon and oxygen burning stages, and material is ejected at very fast velocities. This is the shock wave disrupting the star. On the other hand, impostors are a bit of a strange bunch. By definition, their progenitor or the star survives this explosion. We don't see any of this nucleosynthesis material or any of the material from inside the star, and the brightness of these objects can vary. There is unlikely to be one pathway, more like a zoo of pathways. But the tricky thing is, it's very difficult to tell if the progenitor is there or not. If it's close by, sure, we can observe it and we can visually inspect it. But other times things may be too far away to actually constrain that, or there may be some accountable, such as dust obscuring the progenitor, or not knowing the progenitor star itself, or not knowing the brightness of the star that came before. By some of this material that came from the inner regions of the star can be obscured for decades to hundreds of years from interaction with other material around the star, and this can inhibit these lines or this material from being seen. The intermediate brightness, again, it can depend on the scenario. We have seen very bright supernova impostors that we know the star has survived. So we can kind of rule that out as well. And this high velocity material, the Eta Carinae system showed material moving at supernova-like speeds. So we can't really use that as a definitive test of the star has ended its life. So for the rest of the talk, I'm going to make matters worse by introducing several objects that's initially kind of blurred the line between a supernova and supernova impostors. And for many years, there was no consensus as to what these objects were. So 2 in particular I will talk about that I've worked on a lot for my PhD are 2009 IP and 2016 JBU. I'm just going to explain the naming convention that we use for these. So SN stands for supernova when it is initially classified as a supernova, and AT is astronomical transient. Now these are basically anything else that's not a supernova, something that gets bright on a very short time scale, such as a tidal disruption event or a compact merger, but I won't get into that. But I can just show you that these 2 objects, although they are very similar, which I'll show in a few slides to come, the naming convention wasn't really set because we were so uncertain of what exactly they were. And just on the right-hand side here, I've made a little plot showing what essentially happened with 2009 IP. So 2009 is the year it was found, and you can see on the plot here the number of papers submitted to the archive, which is the website where we can host a lot of our scientific papers. You can see that from 2009 to 2012, you had about 4 or 5 papers on this object. And then I'll show in some later slides that in 2012, in September of 2012, something happened with this star, and the whole astronomical community, the transient community, jumped on these objects, and over the next couple of years, everyone was submitting a paper on this. And you can see there in 2018, halfway through 2018, that's when I started my PhD. So you can see I had about 35 papers to catch up on. And you can see that just that little spit at the end, that's where the focus of this talk will be. So for 2009 IP, this is the light curve. So this is the brightness change of the star. On the y-axis, this is brightness. So smaller numbers are brighter, so it works counterintuitively. Smaller numbers are brighter and larger numbers are fainter. And then the x-axis is just time in days. So you can see the star, or the transient was initially found, and by observing the brightness of it as well as the spectra, it was classified as a supernova, and we started to point our telescopes to look at it and to see how it will evolve. But the issue was it didn't evolve as a supernova. It showed these, what I like to call erratic variability, basically these jumps over the next couple of months. And we said to ourselves, this is not a supernova, although it was classified and the naming convention was put in place and stuck, it was reclassified as an impostor event. And then a couple of months later, it was forgotten about. And then in 2010, it was seen again undergoing outbursts. We weren't really quite sure what was going on here. Maybe it was just the star undergoing something funny, maybe a binary interaction where the star was just having a bit of a tantrum. And then in 2011, it starts to show like severe erratic variability. And it was at this point where the progenitor, or the star itself, received a lot of attention. We really started to follow it up. And we saw that there was very fast moving material in the star was ejecting very fast moving material, something like Eta Carina, but also seen in supernova. So was this a strange type of explosion? We weren't sure. And then in 2012, it did display something that we would assume to be a supernova. It reached brightnesses that we think represent a star ending its life. But under our current idea of how stars live and die, how do we explain all this? Are these 2012 events a supernova, or were they just a massive eruption? And this is where the debate comes in. Is it a supernova or is it an impostor? And this is what my PhD worked on a lot. So if we look into these 2012 events, so we'll just show a little close-up of these. So there's three objects here. One is a supernova impostor, and that's the red squares. 2009 IP, the blue circles, and then a supernova that we know for certain is the death of a star is the green triangles. And you can see that rather than showing one event, one just rise to brightness, 09 IP shows two. So you have the 2012 A event and the 2012 B event. So the star looks to explode twice. And we don't know, or we didn't know, was the A event the star dying and then somehow re-brightening later on, or was the A event something else and then the star exploded during the B event? And you can see that for the red curve and the green curve, brightnesses for both events kind of match each other. So we were really scratching our heads. We were really scratching our heads as to what these objects were. Was this a star ending its life or something more, relaxed yet dramatic? If we look at the later time stuff, so after the object reaches its peak brightness and then begins to fade, okay, let's see, is the star fading as we'd expect a supernova would, or is it doing something funny? And it was doing something funny. So there's a lot going on in this plot, but I just want you to focus on the green points. So these are data points taken in a specific color from ground-based telescopes. So you can see that there's these arrows, and these are the general decay that we'd expect a supernova to follow. So these are how we expect them to fade. And this is governed by radioactive material that was produced when the star exploded. And all supernova, if they produce this material, should follow this decay. But you can see that this arrow and the green markers don't really agree too much. And you can see that the markers even decay slower. And then this green dotted line shows what we think the brightness of the star that came before is. And if you look over on the right-hand side, you can almost, if you squint your eyes, you can see that these points are slowly but surely returning to that value. So we were kind of scratching our heads. It's like, okay, has the star exploded, or is it returning to its brightness before? And if it has returned to this brightness before, that kind of signifies that, okay, the star has survived. It's just undergone some type of outburst, and it's going back to its original magnitude. So you may be asking, okay, this is one object, you know, is it just another Eta Carina? Is it just a very special rare case? This group of transients, this group of explosions is becoming uncomfortably large. So on this is one of the plots for my paper, where I plot 8 of these objects. But since I've actually made this plot, about 10 more have been found. And by found, it's thanks to all these ground-based observing facilities that observe patches of the sky every couple of days, so we can really catch the early time information from these stars. So 2009 IP, which you saw the light curve for before, which is the black markers here, and this object that we're going to talk about a little bit later, which is 16 JBU, both show that in the decade before they explode, something is going on. And there's a bunch of other objects that are showing exactly the same trends, different brightnesses, but something is happening to the star before it undergoes this explosion. If we look at these, the bright events, the ones that we're not too sure is actually the star undergoing core collapse, you can see that they're remarkably similar. They all show these precursor events, which we saw for 09 IP as event A, roughly the same brightness, which you'd expect for a supernova of a certain type or a certain class, and they all show this slow decay, which could signify that the star is going back to its progenitor state, its relaxed state after some time. It remains to be seen, but from the information plotted here, we can't actually tell. So the goal of my work was to explain the observables, so the brightness changes and the spectral evolution and the progenitors themselves of this group of transients, of 2009 IP like transients, using the current stellar theory, like essentially trying to explain these objects without using some black magic. We have a bit of a to-do list. There's a lot to explain in this scenario. I won't get into the majority of this as I've just touched on it very briefly, but the one thing that I will focus on is the last point here, which is what I feel, to make progress in all the other 6 steps, we have to determine, is this a star dying or is it something else? So it might be put that's an either or situation here, but of course things are always more complex than this. And if we go back to the title of this talk, so we use Hubble to reveal the impostor. So our observing strategy is to observe 16 JBU, which we're fairly certain we know what the star looked like before, using Hubble. And we use Hubble specifically because Hubble is a fantastic instrument and it can look at very deep, very faint sources. And we want to determine, has the star finally faded beyond its original state, or has it returned to that state? I'll get into more detail in a second. This next slide I just threw in quite recently because I feel like I talk about these images and they're beautiful and they're colorful and they're breathtaking. But let's actually see what they look like for someone like me when you're actually measuring some science. So on the left-hand side here, this colored image is of what we call the Meat Hook galaxy, which is the galactic host of 16 JBU. It's called Meat Hook because it has a funny naming convention, as astronomers tend to do. It looks like a meat hook that a butcher will use to hang meat. It was named hundreds of years ago. In the green square, that's our region of interest. That's where our star is. And I've just included a little pop-up of that in the lower right. And then on the right-hand side image, this is what Hubble sees. This is Hubble observing in the F55W band, which is kind of what your eye would see. It's called V band for visual. And one thing I'd just like to highlight because I think it's quite neat. If you look at the smaller cutout, you can see this tiny red galaxy just to the lower center of the cutout. And then when you see it in Hubble, you can still see it there. And I just think this galaxy is fascinating because we have the Meat Hook galaxy, which is in the foreground. And then very, very far away, we have the second galaxy just peeking through one of the extended arms of the galaxy itself. I just think that was quite nice, and I just wanted to throw that in. So let's do some measurements. So if we take our image on the right and we do something called photometry, which is measuring the brightness of these sources, let's see how it evolves. So this is the light curve of 16 JBU. The left-hand side shows the early 2016 values. So this is before the star exploded as a supernova, or we'll see. And you can almost see that the light curve is almost showing a periodic tendency, almost like a sine wave. Now, this may be some indication of a binary. You can imagine like an eclipsing binary, or one star moving in front of the other, changing its brightness on somewhat of a regular state. But that remains to be seen, and that's speculation at this point. And then if we look at 2016 and 2017, this is the double peaked event. And this is our bright transient event. And we also see this secondary brightening, which may be interesting, but we'll discuss that later. And then we observed 16 JBU in 2019 to see is it fading beyond its expected magnitude, which on the plot here is this solid horizontal red line. And unfortunately, it was just above it. So it didn't really tell us anything. But as I said earlier, is it slowly returning to its original state, or is it just going to continue to fade? So around Christmas time last year, we got an email from Hubble saying, yep, I observed 16 JBU and I did the measurements and it's gone below its progeniter magnitude, which may initially signify that, okay, source is gone. If we look at the images themselves, which I think is a little bit easier than showing you the plot, we can actually get a handle on how much this star has faded. So for the three panels on the left-hand side, we have the star before it exploded in early 2016 in two different bands or two different colors. If we look at the 2019 observations, as I said in the previous slide, it's kind of returning to its brightness. You can tell by the shapes of the dots themselves. And excuse me, 16 JBU is the object in the center of the frame. And then from Christmas 2021, you can see that the star has almost vanished and is kind of comparable to the noise, but you can still associate that source there with 16 JBU. So these are the optical, or these are the visual bands for 16 JBU. But as I mentioned in one of my slides earlier, we can put something in front of our object and it will change how the energy is received to us. So it'll change the spectral energy distribution. So although it may be faded in the optical, what's to say that there might be some dust in front of the source that is moving photons in the optical out into the infrared? So that's what we looked at. Is the star still there, but from its 2016 eruptions, it emitted a lot of dust, which is something that Eta Carina did. And now this dust is changing how we perceive it. So essentially the surviving source may be hiding behind some dust. So we tried to look into that. So the animation on the left-hand side shows what we did. So the blue curve is a stellar spectrum. So this is how a star emits its energy as a function of wavelength. So you can see that this star emits most of its energy in the bluer side, or the UV, it's shorter wavelengths, and lesser towards the red, which is longer wavelengths. By putting a dust shell, a dust shell around the star, we can reprocess how these photons are received to us through our telescopes. So if you have a blue photon, or a high energy blue photon goes through some dust, it'll come out with a redder appearance. And the important thing here is energy is conserved. So you can see that although we lose energy in the blue, it's re-emitted in the red. So we can take our observations from 2021, run them through this pipeline and see, can we throw any amount of dust into the system to get our observations to match a star hiding behind some dust. So we did that. And this is the plot we get. Okay, so the colored lines, sorry, the plot is a little bit askew. The colored lines are the matching dust model. So that was the moving red line from the previous previous slide. The colored markers are our 2021 observations. And you can see that there is a lot of models that can match a star surrounded by dust. Although we have a lot of information in the visual, nothing in the FAR bands, the IR bands, which I'll return to in a couple of slides. So what does this say? This says that, okay, 16 JBU exploded. It looks like a supernova. Did the star die? Well, we're showing now that it can match a star just with a lot of dust in the way. So this is really promising. This could shake the world of transient astronomy and astrophysics and everything. But then we look at a little more detail. The amount of dust we need is unrealistically large. Now, I say that for a star just ejecting material, a non-terminal eruption. If this was a supernova, yeah, you could produce this amount of dust, no problem. But because we're assuming that the star has survived this, we need a lot of dust. We need 1/10 the mass of the sun to obscure this star to make it match the progenitor model. I was like, okay, maybe there's some unknown pathway to produce this amount of dust. But if this amount of dust did exist, we would see a color change from our 2019 to our 2021 observations. So if you remember, I said that the photon will go through the dust and change its color. As more and more dust is produced, the color is changed by a greater amount, but that we don't see that in our observations. So this all brings us to the conclusion that perhaps emotionally, dust cannot be enshrouding the surviving star. So AT, for an astronomical transient, 16 JBU, is in fact a genuine, albeit strange, supernova. So what else can we do with this? So we know that the star has died. It's undergone a lot of weird stuff in its preceding 10 years or so. Can we explain this without invoking any black magic? So if we compare this to models, so I'm going to get a little bit complex, but let's see how we get on. On the right-hand side of this plot, we have some models of stars that spend their lives evolving how we'd expect them to, and then end their lives in that little red box on the right-hand side of your screen. And we've matched these stars based on the appearance of the progenitor of 16 JBU just before it exploded. Now, this is from a very special library of stellar models called the BPATH models, and it has, I think it's 250,000 different models, and we find on the order of 10 models that match this. So that's not looking good. Maybe we've just found the outliers. When we look into these models a little bit more in detail, we find that all of these stars require a binary companion. So rather than a single star evolving on its own, we need another star to interact with it in some way. And as I spoke about in the beginning of this talk, these are the scenarios that we invoke for both 1987A, the supernova, and Eta Carina, the supernova impostor. So binaries likely play a massive role in how stars live and die. On the right-hand side, I've just shown a plot of how one of these models in particular evolves throughout its life. So this may be difficult to read, but essentially we have two stars, one more massive than the other. As it's more massive, it has a shorter life. It evolves quicker through its life. And there comes a point where it expands into a supergiant. And as a star expands, it gets easier and easier to take material from it. So this expanded star will then transfer material to its companion, and this transfer material changes how it evolves. So if you look at the right-hand side here, where that black arrow is pointing, for a star of this mass, we would roughly expect it to explode with this appearance. And by appearance, I mean a certain temperature and a certain luminosity. And by temperature, let's call it color. So a certain color and luminosity. Well, because of this mass transfer, it actually explodes with a hotter appearance and more bright. And it perfectly matches where we find 16 JBU in early 2016. So let's take this model and let's blow it up. So if we blow up this model using the supernova explosion code, which is a model or is a pipeline that can reproduce how a star will appear to us, we find that it can roughly match how we see 16 JBU. So the green curve here is the model that I showed on the previous slide. And it's not perfect. There's bumps and wiggles, and some bits aren't matching others. And this might just be an issue with our code itself. But the important things are it can match the peak brightness, so how bright this object appears, the rise time, as well as roughly the decline. So this kind of shows that, okay, 16 JBU, albeit a supernova, a strange one, it can be explained by a binary system, which is something new and exciting. And it also gives the opportunity to look for the binary companion, which should survive this, this event as long as the two systems don't merge. So what would we expect? So the plot on the right, the black marker shows where 16 JBU was in 2021. So on the x-axis is color, and the y-axis is brightness. And then the blue marker is where we'd expect the companion. And that's the last point before the primary exploded on the previous plot. And we can see that at the moment, 16 JBU is still too bright. And also the color is not correctly matching the expected companion. Although this might be a little downfall in our models, and maybe more time is needed for everything to calm down a little bit more to actually get a good opportunity to search for a surviving companion. And this is an excellent opportunity to use the Hubble Space Telescope, if it survives the next few years, and the recently launched JWST. Doing a joint operation between these two would be fantastic for a science case like this. So for my final slide, I'll just reiterate what we've done. So if we go back to our to-do list, essentially there's a lot to still be explained. A binary might help things, but there's a lot of other observables that need to be explained. And if it is a supernova, we're missing certain aspects that we'd expect for the death of the star. And we also have weird morphologies, weird geometries that we see. So it seems like the job's not quite done yet, but we're fairly certain that we are watching a star survive in an a star explode and end its life in a very dramatic fashion. So on that, I'd like to thank you for your attention. Thank you again for inviting me to talk about my work, and I'd love to take any questions that you all may have.